This lesson's on the area under a curve and its applications. You're going to be able to find the displacement during a given time interval when you have a velocity time graph, or the change in velocity during a given time interval from an acceleration time graph. And you're going to do both of those things by finding what we're going to call the area under the curve. So first of all, remember the definition of average velocity. Average velocity is the time rate of change of the displacement. In other words, it's the displacement divided by the elapsed time. Rearranging that, we get that the displacement is equal to the average velocity multiplied by the time. And remember that the average velocity and the instantaneous velocity are going to be the same when velocity is constant. Let's take a look at this example of a velocity time graph. It's going to be important that we always check what the variable on our y-axis is when we do these kinds of problems. So here is the time axis along the horizontal, and we see this velocity time curve. We're going to call it a curve even though it's made of straight line segments. Curve's just a generic term. So what's happening here? Well, we've got an object that's moving 2 meters per second right, or if we define right as positive, at positive 2 meters per second, and it's doing so for 5 seconds. Well, if you travel 2 meters per second, that's 2 meters every second, and do that 5 times, you end up traveling 10 meters, in this case 10 meters right. What we're actually doing when we do that is we're calculating the area of this rectangle, the area between the curve and the time axis. This height here is our 2 meters per second, and this length here is our 5 seconds, and we're multiplying those two together. 2 meters per second multiplied by 5 seconds is 10 meters. In other words, we're multiplying our average velocity by our elapsed time, and we're getting our displacement. This 10 meters is positive 10 meters or 10 meters right, because that's how we've defined the positive direction. Again, what we've done is we've multiplied our time by our average velocity, and we've gotten our displacement. The area under the curve of a velocity time graph gives the displacement. Let's do another example. Again, we see that we've got velocity on the y-axis, time on the x-axis. In this case, notice that two things are different from above. First of all, the velocity is not constant, it's changing. And second of all, notice that we are moving in the leftward direction. The velocity here is always negative if right is positive. Then this object is moving to the left. It ends up moving negative 4 meters per second or 4 meters per second left, but it doesn't start off that way. So this is where this approach of finding the area under the curve really becomes most helpful, because the previous example was pretty straightforward, just multiply two numbers together. The same process applies, however. We've got this area, and it gets called the area under the curve, but that can be confusing at first. It really means the area between the curve and the time axis. So if we find this area, it's a triangle. So a triangle is 1/2 times the length of the base. In this case, that's 8 seconds, multiplied by the height. The height here is negative 4 meters per second. Multiplying those two together, I end up with negative 16 meters, or 16 meters to the left. That's the displacement that this object has gone through from time 0 seconds to time 8 seconds, and actually it just stays there until time 10 seconds as well. So although we call it the area under the curve, it's really the area between the curve and the time axis. And I'm also going to call it the signed area under the curve, because here this area is negative 16. And that means that we've got in this case, a leftward displacement. So the signed area under the curve on a velocity time graph gives us the displacement. Let's do one more example with velocity time graphs before we move to acceleration time graphs. So here we've got both a positive area from 0 to 5 seconds and a negative area from 5 to 10 seconds. Well, the area of this is 5 by 2 or 10 meters, whereas the area here is the length is 5, 10 minus 5 times negative 2 or negative 10 meters. And so if I ask what's the displacement from time 0 to time 10 seconds, the displacement is just 0. This object ends up back where it started from. If you think about it, it's moved 2 meters per second to the right for 5 seconds, and then turned around and moved 2 meters per second to the left for 5 seconds. So it makes sense that it ends up where it starts from. We add these two areas together, and because they have signs with them, we end up back at 0. Let's do an example now with an acceleration time graph. The units on the vertical axis are meters per second squared. This 2 should be a superscript, and on the horizontal axis are seconds. Notice that when we multiply meters per second squared, which is going to be our height of any area, by seconds, which is going to be the length of any area, we get meters per second, the units of velocity. So if we first take a look at this triangle here from 0 to 6 seconds, we have a height of positive 3 meters per second squared, and we have a length of 6 seconds. Multiplying those two together and dividing by 2, we get positive 9 meters per second. Now, that's not the velocity, but it's the change in velocity over those first 6 seconds. Similarly, the area here over the next 3 seconds is negative 3 meters per second. And so if I look over the whole 10 seconds, the change in velocity over that whole time is positive 6 meters per second, or 6 meters per second to the right. Again, that doesn't mean that that's the final velocity. It's the change in velocity. So let's say that this thing started off moving at 10 meters per second to the right. Now it's got an additional 6 meters per second to the right of velocity, so it's traveling at 16 meters per second. Let's say it started traveling at negative 10 meters per second to the right, or 10 meters per second to the left. Now it's traveling at negative 4 meters per second, or 4 meters per second to the left. It's the change in velocity, not the velocity itself. Let's summarize. The signed area under the curve on an acceleration time graph gives the change in velocity. Also a bit of a review. The slope on a position time graph we know gives us the velocity, and the slope on a velocity time graph gives us the acceleration. The slope on an acceleration time graph gives us the rate of change of the acceleration, but we're not going to worry about that.
Similarly, we've just found that the area under an acceleration time graph gives us the change in velocity. And the area under a velocity time graph gives us the change in position. And change in position has a special name. We call that the displacement. Now, the area under a position time graph doesn't give us anything physically useful. Now, therefore, if you think about position, velocity, and acceleration as a kind of continuum, then taking the slope moves us in this direction. Finding the slope of a position time graph gives us the velocity. Finding the slope of a velocity time graph gives us the acceleration. And finding the area under the curve moves us in the opposite direction, where finding the area under an acceleration time graph gives us change in velocity, and area under a velocity time graph gives us change in position. Just as we said that finding the slope is the interest of an area of calculus called differential calculus, finding the area under the curve is the interest of another kind of calculus called integral calculus. So that's a summary of area under the curve and its applications.